This is Dr. S.P. Harsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 19 on the course of Strength of Materials, and this course is developed under the National Programs on Technology Enhanced Learning (NPTEL). Prior to start this lecture, I just want to refresh, in whatever we discussed in the prior lectures, in the previous lectures as such. In the previous lectures, we discussed about that when we have a thin cylinder, then what the types of stresses which are inducing when it is subjected by the internal pressure P, and we found that there were two dominant the stresses were there and corresponding strains were there, like the longitudinal stress and longitudinal strain, and the other one is the hoop stress, or we can say rather it's a circumferential stress and circumferential strains. And then what the interactions are there. So, if we want to compute simultaneous effect, then we consider the Poisson ratio, and then we also discussed that actually when these two types of stresses or the strains are there in a thin cylinder, then how we can compute the total volumetric stress and volumetric strain particular. And then we found that in the volumetric strain there were contributions from both of the strain component, like the longitudinal plus 2 times of hoop or circumferential strain, if you want to compute the volumetric strain. And then we were trying to see that if we have a thin cylinder without the two extreme corners of any spherical or any kind of shape, or if we have the thin cylinder with the spherical shape, then what the differences are there if the spherical shape has different thickness and the thin cylinder wall is having a different thickness. So, this kind of relations which we developed, and then we found that actually if this thin cylinder or a shaft is just subjected by a twisting moment or a torque or couple, then we derived that this only whenever a shaft is rotating, or if it is not rotating and only there is a kind of twisting moment is applied, then there is a pure state of stress is acting in these cases. Because in the previous case we found that whatever the longitudinal and these hoop stresses are there, they are mutually perpendicular to each other, but they are only the normal stress component. But whenever there is a torque applied, then only the kind of shear stresses are acting and the corresponding shear strain is there. And also we were trying to develop the relationship in between those stresses, that actually what will happen if these kind of stresses are there, that what is the shear stress. And since we are talking about the shear stress and corresponding shear strain, then we found that there is one shear modulus of rigidity is there to compute that part. And at the end also we found that if we are talking about a shear strain, but if we have a spring component, then it also exhibits the similar kind of trend as we found in a previous case, like in this solid bar or any kind of rod or shaft is there, and if it is under the action of any twisting moment or couple. So, even we have a spring, then similar kind of twisting moments are occurring, and it depends on that what the number of coils are there, and how much torque is applied, and what will be due to the under the application of these torque, or due to the application of this torque, what will be the maximum shearing stresses are inducing, and then what the shape or the sizes are there of the different types of coils. So, all these are, if you want to design either the circular shaft or either the bar or even about the spring, then these are the key parameters which always one has to consider just to for the safety measures, or if you want to strengthen your either the bar or the springs kind of that. So, this kind of discussion which we have already made in the previous lectures, and we also found that that whenever there is a closed the spherical shapes are there in in the thin cylinder, then there is a chance of the distortion, or there is a chance of the maximum deformation can be occur wherever the joint points are there, or wherever these the two different sections are clubbing together. So, to remove that, actually there was a standard the thickness ratio was there, and if we are keeping the thickness of this cylinder wall is 2.4 times the thickness of the spherical walls, then we found that there is a very less chance to be having a kind of distortion at the junction point. So, this these are all the real key points, and also I just want to prior to start the next lecture, I just want to refresh your formulas also, that if you are measuring the longitudinal strain, then again you see the key parameters are this p times of pd divided by 4 times of e into t into 1 minus 2 mu. So, because you see like these are the key formulas. So, while solving the numerical problems, one has to remember, and then you see like if we are talking about the hoop stresses, then it is epsilon 2, which we are like denoting in the previous lecture, and that is nothing but equals to pd by 4 te into 2 minus epsilon. And if we are talking about the volumetric strain, and as I told you recently that actually volumetric strain is nothing but equals to this longitudinal stress plus 2 times of hoop stresses. So, again you see we can simply compute that pd by 4 te into 5 minus 4 times of this Poisson ratio. So, these three are the key like formula, and then you see if you are talking about the thickness ratio, then again depends on absolutely, as I told you that we have to be very much careful by taking like that what the spherical the ends are there and what exactly the thin cylinder is there, the walls are there. So, even you see the T1 by T2, the T1 if the wall thickness of this cylinder, and T2 is the spherical walls are there at the extreme end. If T1 by T2 if you want to compute, then it is nothing but equals to 1 minus mu divided by 1 minus the 2 minus mu. So, you see by keeping the mu is nothing but a property of the material, and if we are talking about the mild steel, then we were using 0.3, or if you see the different kind of like the material is there, then Poisson ratio is different. But again you see there is a limiting part is there for the Poisson ratio, because Poisson ratio is simply computing the lateral strain by the longitudinal strain. So, again you see we have to like concern that which material we are using, and then corresponding what the thickness ratios are there, just to avoid the kind of distortion at the junction point. So, you see these are the key features which we discussed in the previous cases, but now you see again we are going to discuss that actually whenever a shaft is there and when it is twisting, and definitely you see as we discussed that actually like the twisting moments are there, and you see because of the twisting moment or the couple or the torque like the shearing stresses are there, and there is a maximum shear stress is there which you need to consider, and then the two other parameters are the size and the shape of a material, or we can say an object. So, again you see if you are talking about all these parameters, then again we found that the shear modulus of rigidity is again a key parameter, and to compute that, since the Young's modulus of elasticity in like in the normal stress and strain component is a basic property of material. So, similarly you see here if you are talking about the shear stress and shear strain, the shear modulus of rigidity is again a key feature, and it is a property of material. So, which material you are using, corresponding values are coming for the value of Z, and Z is nothing but equals to the shear stress by shear strain, or we can say tau by gamma. So, again we are computing here like the shear stresses which are coming due to the torque, and we are also measuring the corresponding distortion in the material due to the application of the shear forces. So, you see since we are computing and we are saying that you see like the shear modulus of rigidity as well as the Poisson ratio is absolutely occurring within the phenomena. So, we are saying that the Hooke's law is valid for those kind of deformation, or we can say that the elastic deformation is there. So, we are not going beyond the region, only our discussion is well defined the period of the elastic region. So, that is why you see all either the elastic modulus of this rigidity, or this Young's modulus of elasticity, or we can say that the bulk modulus of elasticity or the Poisson ratio, all four like the parameters which are very much valid for the elastic deformation is applicable, because we are only applying the load for the Hooke's law. So, now you see here whatever we discussed in the previous lecture, now we just want to derive in forms of the mathematical formulation. So, again we are going for the torsional formula. So, here you see like we are starting with the simple torsion theory. So, basically like we are interested to derive an equation between all the relevant parameters which we discussed. We discussed that actually we have a circular bar and we are applying the torque. So, due to the torque the shear stresses are there, and due to the shear stress there is due to this shear stresses which are occurring on the circumferential part of this bar. So, due to that there is an angular twist is there, and due to the angular twist we have a resultant shear strains are there. So, if you just go by one, then you will find that we have a torque which is applied on this circular bar, and due to this torque we have a shear stresses which are inducing due to the application of this torque. So, tau is there. So, starting from T to go to the tau, and then when we have a shear stresses, definitely the corresponding shear strains are there, because due to this shear stresses we have a angular twist is there, and due to the angular twist what we have a distortion, and we want to measure the distortion. So it is nothing but we can only measure by the shearing strain. So once you have shear strain, once you have the shear strain, so shear stress and shear strain can be computed with the using of shear modulus of rigidity. So G is there. So now you see, with all those perfect parameters, we just want to relate these specific parameters. So the relationship in the torsion will be coming as T by J is equals to tau by R is equals to G theta by L. So now you see, you will find that there are three different terms, and these three terms are exactly equal. So what this term signifies? So these terms signifies that we have the first term, which is T by J. So the first term refers to the applied loading, that actually what exactly the torque is there, how they are applying, in which direction it is to be applied, and when the torque is applied, you see what the corresponding property of the section is, means what is the affected area is. So you see, like if I am saying that T is the torque applied and J is the polar section of moment of inertia is there. So what is the area moment, means actually here what we are taking, we are not going for the mass moment of inertia, we are going for the area moment of inertia, and since it is a polar section is there, so what we are doing here, we are simply dividing by this T by J. So whatever the property which is getting, it is exactly equal to the second part, the second term, which is coming as tau by rho. So you see, the tau is nothing but the shear stresses which is coming due to the application of this torque. So you see, the shear stresses are there, and if you are saying that the shear stresses is there which is increasing as we increase the radius. So you see here, this is a quite significant part is there, that if we are starting to apply the torque, always, as I told you, that it is increasing from like center point, and it is at maximum at the circumference part is there. So this relation is very much like valid, that actually as we move further, means as we starting from the centrifugal part, the origin, and as we are moving towards the outer circumference, then we found that actually it is simply increasing, and it is the maximum at the outer periphery of this cylinder, or we can say the rotating shaft. So this as you move like, or as you increase the value of R, the shear stress is also increasing. So these two sections, T by J, which is exactly equals to tau by R, and then the third term gives the relationship between the shear modulus of rigidity into the angular twist divided by the L. So third term refers to the deformation, and that contains the term of modulus of rigidity, that is Z, and the combined term of the angular displacement, that is theta by L. So which is nothing but equivalent to the strain for a purpose of designing a circular shaft to withstand a given torque. That means, you see, whatever the torque applied is there, then how much the relative displacement is there in terms of the circumference with the corresponding to the length of the bar. So you see, this will give you a clear cut feeling that actually, since if we have like more and more this length is there, if you are increasing the length of like starting from 0 to 1 to, and if you have the 10 millimeter of the length of this bar is there, so at the extreme corner you will find that the more angular twist. So generally you see, like if you remember the previous case, then we found that if AB was the length is there, you see in the like in the circular bar, in which you see whenever there is no loading condition is there, so all those layers are well set up within the this circular bar. But as we apply the torque, you see the B was shifted to B to B dash, but that B to B dash shifting was at the extreme corner, but whatever the A was there, you see it was exactly at the same point even after the loading. So the meaning is pretty simple, that as you like move this L to as you are moving to the L right from the origin to the extreme, and then you will find that the theta is also increasing, and since you see now like the distortion is more, so you can simply capture this kind of distortion or the deformation in terms of the strain, and this strain is known as the shear strain. So the meaning is pretty simple, that all those terms are well signify that if we have T by J, which is exactly equals to this tau by R, which is exactly equals to Z theta by L. So T by J is also giving you the similar kind of feeling, that as like when you apply the torque, the effective area is always maximum whenever you are at the extreme end. So whatever you see, the polar moment of inertia is there, it all, as you increase those things, you see, like the torque is also, the effect of torque is also more. So all three terms are giving you the similar kind of feeling, and that's why we can say that for any kind of rotational shaft, this formula is very well valid. So now you see, we must develop an equation which is giving the relationship between the twisting moment, maximum shear strain, produced because of the shear stresses are there, and a quantity which represents the size and shape of the cross sectional area of the shaft. Because you see, if you know the cross sectional area of the shaft based on what the size and shapes are there, then you can also find it out that actually how the distortion can be taken place, or we can say the how these microstructures are to be disturbed whenever the torque is to be applied on this circular shaft. So that's why you see, we can simply signify that actually all these three terms are very much valid whenever like the torque application is there on a circular shaft. So now you see, we just want to visualize those concepts which we discussed recently, that we have a circular shaft, as you can see on the figure on the screen, and this circular shaft is rigidly fixed at one corner, and this at another corner it is free. So now what we are doing here, we are simply applying the torque in this clockwise direction. So you can see this on this particular extreme corner, that there is a load application, or the torque application is there on this free end. So due to the load application, you see this torque will always try to tend the shaft in a respective direction. So you see, our shaft is having like the kind of rotation, it has a tendency to move towards this direction wherever the torque application is there. But you see, if we are saying that under the torque application, if our shaft is in equilibrium position, so definitely you see we have a resisting torque exactly equal and opposite to the applied torque. So then we can say, when you are applying the torque, there is the internal mechanism is there because of the microstructure of this uniform bar, through which we can simply apply, or we can say through which the microstructures are always trying to put an opposition force to just balance whatever the disturbances are there. So what we have, you see, if you are simply cutting a portion, which you can see here, we have a simple segment. So if we want to analyze the segment, then we found that this applied torque, due to the applied torque, now you see here, this is a tendency to moving a kind of section. So whatever the microstructures, or we can say the layers are there of this particular shaft, they will just tend to move here. So what we are doing here, we are simply taking the small section of this particular bar, and we found that after observing that particular phenomena, we found that all those right from the elements which are lying along the center line of this particular C here, they have the less tendency, but as we moving from center to outward direction, that means on the circumference, we found that this particular tendency to move in a particular direction, that means where the torque is applying, they have more tendency to move in that. That means you see the effect of the torque is more on the circumferential side rather than it is on the this axis part. So that's what you see, the shear stresses, whatever the shear stresses are generating, they are always not along the axis, they are always along the circumference, or we can say they are always along the plane part. So here, due to that, you see, due to the rotation, now you can simply see that we have a shear stress which is applying in this direction. So this, you see, this is the shear stress which is inducing because of this torque. So but if we are saying that this shaft is in well balanced, it is in equilibrium position, so definitely there is a counter this, or we can say the counter torque or the resisting torque is there. So this is, you see, the resisting torque is there, and this is resistant torque which is coming, and due to that, you see what we have a complementary shear stresses are there. So what exactly things are? Due to the torque, we have a tendency in an object that to put the shear forces. So you see here, these are the applied shear forces, the applied shear stresses are coming due to that part, due to this particular applied torque, and the corresponding due to this resisting torque, we have these complementary shear stresses are there. So this is the applied shear stress, this is the complementary shear stress, and if they are and if you see the notations, then you will find that this has a tendency to move the object in a clockwise direction, and this has a tendency to move in a just repulsive direction. So if your shear stress and complementary shear stress, if they are exactly opposite and equal, then only we can say that the total this whatever the under this particular our bar it is exactly equilibrium, or we can say just they can maintain the equilibrium under the application of these combination, these 4 combination. You see, like you see, if you see this part, you will find that they are acting in this particular opposite direction and they are opposite in this particular direction. So under the application of these 2 forces, or we can say these 2 shear forces or these 2 shear stresses, this is well perfectly balanced, and this diagram is clearly showing this kind of phenomena, that we have a applied torque, we have a resisting torque, we have a applied shear stress, we have a complementary shear stress, both are acting on the same time, both are exactly equal and opposite. So whatever you see the torque application is there, or whatever the shear stress application is there, we can say that this whatever our this uniform bar is well balanced under the application of these torque or these shear stresses. So this is the exact phenomena is there, which we want to discuss. So this is what actually we discussed. You can again gone through from the this written material, that when a uniform circular shaft is subjected to a torque, it can be shown at every section that shaft is subjected to a state of pure shear, that you see the applied shear part was there, and the moment of resistance which has to be developed by the shear stresses being everywhere equal in the magnitude and opposite in the sense of the direction. So you see, if it is there, that is what we are saying, that the resisting torque is there when the applied torque is there, and when applied shear is there, the complementary shear stress is there, just to balance those things. And for the purpose of the deriving a simple theory, we need to describe the behavior of shaft which is subjected to a torque. It is necessary to make certain assumptions, because you see we cannot say if you go for the realistic situation, then you always find that whatever the distortions are there, and which we are measuring that the distortion, it is just uniform starting from 0 to maximum at the extreme corner, but certainly you see it is not in practically it is not there, because whatever the displacements are there of the microstructure from one part to another part, it is not uniform, because even the torque is applying, but this torque is one has to be assumed that this torque is uniformly distributed all across the cross section of this particular circular shaft, and also with that whatever the tendency of the material is there, it has to show a clear the similar kind of strain whenever the the torque application or the shear force applications are there. And then immediately, if we are saying that we are going up to only the elastic deformation, then whatever the torque, due to the torque, whatever the shear stresses are inducing, one has to exhibit the complementary shear stresses exactly in a equal amount in magnitude and in the opposite direction. So there are lots of ifs and buts are there to apply this kind of theory. So one has to make certain assumptions prior to derive those relationships which we have shown in the first slide. So here some of the assumptions are like that. First of all, the basic thing for every kind of theory in which we are assuming that and even actually when we say that the generalized Hooke's law is valid, one has to consider that whatever the material is there, it is to be homogeneous and it is to be isotropic material. With that you see whatever the shear shearing directions are there, or whatever the components are there of the these stresses, normal and shear stresses, they are supposed to be equal in all the directions. So coming to that point, for the generalized Hooke's law, here also we are applying the similar kind of theories here. So that is what we can say, that first the material is supposed to be homogeneous, means it is must that material is homogeneous, that means the uniform elastic properties are to be existing throughout the material. That means there is no kind of nonlinearity is there in between the stress and strain, or any kind of the elastic properties of that particular material. So first the material is supposed to be homogeneous, second the material is elastic, follows the Hooke's law. So with the shear stress is proportional to shear strain, then all you see we can say that the Z, which is the shear modulus of rigidity, is valid, because if you see if you are saying that your material is not elastic or it is not showing exactly the ductile material property, then you cannot exhibit the proportional limit, or up to you cannot go up to the yield limit, and then you cannot say that you see all the Young's modulus of elasticity or shear modulus of rigidity or this shear stress strain, you cannot make the relationship, because if the stress is not proportional to strain, or we can say if they are not showing the linear relationship, then you see all those formulas which we are deriving is absolutely incorrect. So both are, either the material is homogeneous or material is supposed to be within the elastic deformation. These two are the biggest assumptions are there. Then certain more assumptions are there, like the stress does not exist like exceed the elastic limit, because once it is going in the plastic deformation, there is a permanent set of deformation is existing within the elastic, within the material. Then you see, even if you release the load, body the whatever the object is there or the circular shaft is there, there is a permanent deformation or the distortion is there. Then even if you apply the load, it will exhibit more and more kind of like the distortion. So you see, we need to put our load up to the elastic region only, and then you see we have a the circular cross section remains circular, because you see, once you cross the elastic limit, definitely the distortion is there, and due to this distortion, the circular cross section of the shaft will be either in elliptical or any irregular shape is there. And then we can say that, you see, like whatever this theory which we are assuming, we are assuming with the uniform cross section with the uniform stress distribution, so which is not at all valid. So this is one. And then you see the fifth assumption is the cross section remain plane also, because if you like if it is not planar, then definitely whatever the stress distribution is there within the within this total cross sectional area of the circular shaft, which will not be remain same. And you see the stress concentration or any other like the phenomena or any other properties are there, and they are different like altogether. And you see, in the first, even we are saying that since the material is homogeneous, so it has to be exhibit like all the elastic properties through the common, or we can say the uniform all across the material. And the last assumption is the cross section like the rotate as if it is rigid. That means every diameter rotates throughout the like this particular this rotation at the same angle. Because if you see, there is a different cross sectional areas are there, or even you see if you have a same cross sectional area, but if it is rotating at a different angular twisting, then definitely see whatever the angle of twist is there, the theta, which will not uniformly deform. And you see, since our whole measurement is absolutely based on the theta, because even in the formula you will find that the g theta by L is there. So the theta is very, very important parameter, because whatever the distortion is there, and if it is not uniform all across the body, then whatever the shear strain, because what we are doing here, we are simply checking with the angle of twist only. So whatever the distortion is coming, it is coming due to the angle of twist theta. So if any irregularity is there in that particular rotation, so obviously the shear strain is not coming exactly which we want to measure. And once you don't have the proper shear strain, then you cannot say that this shear stress and shear strain relations are proper, or whatever you see like the formulas which are coming under the Hooke's law, they are valid. So one has to be very clear that actually the first of all, your circular shaft is uniform throughout the cross section, and it is to be rigid. There is no hollowness is there, and there is no weaker sections are there, that okay, the shaft is weaker at the central position and rigid at the outer part, or vice versa. Then definitely you see this shaft will rotate at different angles, and definitely whatever the angular twist is coming or the shear strain is coming at a particular section, they are absolutely different altogether. So these assumptions are very, very valid if you want to like apply that kind of theory where we are saying that the T by J is equals to this tau by R is equals to G theta by L. And once you like you want to apply this theory, one has to first satisfy these assumptions, and then you can apply this theory. So you see here, come to the main point, as we like discuss that if we if we are applying the torque on a circular shaft, then what will happen, since as we discussed that actually like this is the applied torque, and here the resisting applied torque is like generating here, and if you are saying that this is the length of this bar is there, so obviously like it is starting from this this angle of twist, and it is maximum at that. So you see, if you want to measure that how much distortion is there, always we are measuring from this this point to this point. So now you see, earlier this point was A, and now you see A to B, these layers are shifted from this point to this point. So we are measuring in terms of angle of twist, and if I am saying that this point O is the origin is there from where the central axis of the shaft is passing, then we can simply say that this is my radius capital R, and this is my angle of twist, that is theta from A to B. So this arc is there, okay. And if I want to measure in terms of the distortion, obviously the shear strain is there, and shear strain is nothing but equals to gamma. So this figure clearly signifies that whenever the angular twist is there, always you see there is a kind of distortion, and which is maximum at the end, starting from the 0 where the rigidness is there, and which we can simply measure with the angle of twist. So this theta is there. So as we see in the previous diagram that there is a solid circular shaft is there which has a radius of r, and like the torque applied at the free end. So the fixed end was like the free end, as I told you that like when the applied torque is there, the free end, there is a resisting torque is coming. So under the action of this particular torque, we found that there is the radial line is there at the free end, which is just showing the twisting is there at the extreme end, and the twist which we are measuring as the this angle of twist, that is the theta at point like A to, if we are moving to B. So A to B is a circular point is there, and we are saying that the arc AB is there, and we just try to set up the relationship between in this arc AB, because when it's starting from O to A, this will move from A to O to A to O to B. So this is a kind of measurement, or this is a kind of angular twist is there, in which we are saying that this is the theta, and O to A is the circular radius is there, that is the capital R. And if you are taking the substantial amount of this twisting, we are always measuring a kind of distortion as far as the total length is concerned, L as, so this is coming as the gamma, that is the the total distortion. So this we can say the angle of distortion of the shaft all along the line is always the shear strain is there. So now we would like to set up the relationship in between all those the kind of this applied torque and all those things. So here you just go to the basic part that you see at the extreme free end corner, what we had, there is a twisting is there right from O to A to O to B. So AB this arc is there. So angle in radians is nothing but equals to arc divided by whatever the radius is coming. So arc AB is nothing but equals to the radius, that was theta, and the angle of twist is there, that the radius is r, and the angle of twist is there, that is the theta in terms of the radians. So this is just for the outer periphery of that, but if you are going for all along that part where you see this total length L is there, and the shear strain, or we can say the total distortion is coming in this particular shaft, where there is a shifting is there of the layers right from this free end to the resident corner. So we found that this arc AB is exactly equals to r into theta, where the frontal portion is there, and you see if you are going for the circumferential, then it is exactly equals to the length L into the shear strain gamma. So you see if you are equating, since the arc AB is exactly equal to both the things, so if you equate both the this angular twisting, then you will find that r theta is equals to L into gamma, where r is the radius of this circular shaft, theta is the angle of twist, and L is the total length of the circular shaft, and gamma is the shear strain which consisting the total distortion of this particular shaft. Then you will find that we have the shear strain gamma is equals to r theta by L. So this is, you see, the from the definition of a modulus of rigidity, now we can simply say that you have the shear strain, you have the shear stress. So you can make the main relation between these two terms, the shear strain and shear strain, with the using of shear modulus of rigidity. So under the the load application of this Hooke's law, or we can say under the this elastic limit, we can say that the shear stress is proportional to shear strain, or shear stress is equals to G times of shear strain, or G is equals to shear stress by strain. So you see this relation is there, shear stress is equals to this modulus of rigidity is equals to shear stress tau divided by shear strain, as I told you recently, where this gamma is the shear stress which is to be set up whatever you see at the radius of r. So just by equating those things, what we have the shear strain gamma is equals to the shear stress divided by G. So you see from here this gamma is nothing but equals to this G will come in the denominator side, and on top of side we have this tau. So tau by G is gamma. But you see if you go to the previous section, then you will find that this gamma is nothing but equals to r theta by L. By equating r theta and gamma L, what we get shear strain is equals to r theta by L. So now you see if we are equating both the term here, this equation which is tau by g and the previous equation, that is r theta by L, what we have a relationship in between these two terms, that in terms of the shear strain is r theta by L is equals to tau by z, or you see like in that term you see we can say that r, this tau by r, this tau if you take it by r is equals to z theta by L. So this relation is there, is valid for the outer radius of that. But if you are talking about the inner radius or any radius which is at r dash, we can say that tau by small r, or this tau dash by small r, if I am saying that the tau dash is the shear stress any radius small r, is equals to tau by capital R, which is recently we have shown that if we have a solid shaft and it has only one radius, that is r, the shear stress is tau. So tau by r is equals to z theta by L, or it is also equals to tau dash by r. So you see, if you just remind that actually on the first slide, I have shown you that we have a relationship between like all three components. So for the second and third terms will be you see tau by r is equals to the third term, which is g theta by L. So you see this we have proven here. So now as we move further, because we just want to like set up all three equations, so for that now we are considering the circular section of that particular shaft. So here just by considering the small tip of the radius on that circular section, and also we are just cutting the portion of the small segment, and it has a thickness of delta r. You can see this particular figure which is subjected to a radius, which is subjected to a shear stress tau dash. So again you see what we have a circular section, and only we are, because we are simply assuming that this whatever the distortion or whatever the shear forces are, shear stresses are coming under the action of shear forces, they are uniformly distributed all across the cross section of the area. So here you see what we can do here, we are simply taking, this is origin and this is the circular portion, and it has you see like the radius is small r, and if I am considering a small portion like that at the radius small r, what I have like the shear stresses due to the torque application is tau dash. So this is the tau dash, directions are there, and this segment which we are considering for our this study purpose, the segment thickness is delta r. So you see now if we want to set up the force on this particular element, then the force set up on this particular element is nothing but equals to the stress developed under the action of this applied torque into the area concerned. So you see, since stress is nothing but the tau dash which we are already taken here, and the area, because it is a circular section, so the area is 2 pi r. This is the 2 pi circumference is there, 2 pi r into the thickness dr. So now my area is 2 pi r dr, or generally we are taking t here, but we are taken here as a small element and dr is the thickness. So 2 pi r dr is the area and the tau dash is there. So force is nothing but equals to shear stress into area, so tau dash into 2 pi r dr. So once you have the force, then this force will produce a moment, because our torque about the central axis to resist that part, because you see like when you apply the torque, these shear stresses are forming. So now you see due to the internal reactions, always they are supposed to set up the kind of this torque, or we can say the moment exactly applied to this applied torque, and that is why we are saying that this is the resisting torque, or we can say the twisting torque again that applied torque. So this is nothing but equals to tau dash into 2 pi r dr. So tau dash is the shear stress, 2 pi r dr is the this area. So this tau dash into area is the force, and force into this radius is the moment. So tau dash 2 pi r dr into r will be the just opposite torque is there, or if you are computing the moment or torque, then it is exactly equals to 2 pi this tau dash into r square dr. Now this torque is simply applying on this particular section, but you see as we are saying that whatever the distribution is there, irrespective of the shear stresses or irrespective of whatever the forces are there, all across the layers or the microstructure of this particular shaft is uniform. So you see, you can simply compute this torque for the whole section, because this whatever this moment which we are gaining, it is just for the small this section which has a thickness of dr. So now if I am saying that this is very well valid for all across the section, so now the total torque on that particular this circular shaft is nothing but the sum of the contributions contributions from these small section of dr. So T is nothing but equals to integration of 0 to r for like starting from central axis to the extreme corner r, the integration of 0 to r 2 pi 2 pi into this tau dash r square dr. So 2 pi tau dash r square dr will be coming, and now we are computing this is for the small section, and we are computing for all across this, where you see the tau dash is a function of r. Obviously like this tau dash, as we have clearly shown in the previous figure, tau dash by r. So tau dash is a function of r and it varies with the radius. So like we can simply write the tau dash in terms of this particular first equation. So it will come exactly as tau dash by r is nothing but equals to g theta by l, as we have shown in the previous equations by equating tau dash by r and that. So tau dash is nothing but equals to g theta r by l, and now you see if we are like keeping in the previous equation what we have, the total torque T is nothing but equals to 0 to r 2 pi instead of tau dash. Now I am simply writing, because tau dash is a function of r, so we need to describe this tau dash in terms of r. So you see here we are simply replacing this tau dash in terms of r, g theta r by l. So and then you see r dr was already there. So now what we have 2 pi g theta by l r square dr, or what we can r cube by dr, or what we can do here, we can simply take it out all those component at outside. So we have now 2 pi g theta by l, these are the constant terms. So if you look at these figures, then you will find that the g is the shear modulus of rigidity, which is a material property, theta is the angular twist. So once you measure the angle of twist, then it is constant, and then l is the length, which is like the constant for all across the like this particular body, and even under the application of load also. So now you see what we have, the torque is the variable function of r cube dr under the integration of 0 to r. So now you see like after integrating that term, what we have T equals to 2 pi g theta by l into r4 by r. After integration, r cube dr is nothing but r4 by r, and 0 to r, which we need to apply the definite integral. So after keeping these like values, what we have g theta by l into 2 pi r4 by r, or we can say that after cancelling 2, what we have at the end g theta by l pi r to the power 4 divided by 2. So now you see here, if I am replacing this r by the total diameter of the circular shaft, then r is nothing but equals to d by 2. Since we have r to the power 4, so what we have at the end, we have the torque is equals to g theta by l pi d4 by 32. So now you see like as we were discussing about, we have this polar moment of inertia. Polar moment of inertia is nothing but equals to what will be like whatever the effective area is there under the application of the torque. So J is nothing but equals to pi d4 by 32. So whatever the component which we have right now, pi d4 by 32, can be easily replaced by J, and J is the polar moment of inertia, because it is coming under the concerned area or the defected area. So you see here what we have now, we have the torque which is equals to g theta by L into J, or we can also equate T by J, the applied torque divided by this polar moment of inertia is equals to g theta by L. So now you see like this relation is well set up, that in the previous equation what we had tau dash by R or even tau by capital R was equal to g theta by L, and here we have T by J equals to g theta by L. So g theta by L is equals to this tau by capital R, or we can say tau dash by small r, means whatever the shear stresses are there at a particular section R, which is equals to T by J. So here you see what we have the final relations which we like started from the beginning, that if we have like the solid circular shaft which has a uniform cross section, having this homogeneous material property, and which is under the application of elastic loading condition or elastic deformation, and it has like the uniform cross section, through that whatever the angle of twist is coming or the shear strain is coming, it has to be uniform. And then you see like it doesn't have the different cross section throughout the particular this length. So under all these assumptions, we can simply derive that when a solid circular shaft is under the angular twist is there, this we have this shear stresses at a particular radius tau, and due to that you see the angular twist is coming as a theta. So these all these technical terms are summing up with the kind of relation as T by J is equals to tau dash by r is equals to g theta by L. So this is a very well relationship you see, and we can simply derive for this kind of shearing stresses. So now you see in this particular condition what we have the torque which is the applied external torque which is constant over the length L. So you see here this was the biggest assumptions which we were assuming that whatever the torque application is there, it has to be uniform, okay, and it doesn't vary as with the time. So this is kind of so called the static torque is there, and J is the polar moment of inertia. And if we are using the solid shaft, then as we have discussed already that it is based on the area, so it is pi d 4 by 32 for solid shaft. And if we have a hollow shaft, that means you see if we are simply removing a portion from this solid circular shaft, so we have some hollow circular section. So for that you see we have a two different diameter. So if we have a d is the outer diameter and this small d is the inside diameter, so we can derive the J, the polar moment of inertia for hollow shaft also, which is nothing but equals to pi capital D to the power 4 minus small d to the power 4 divided by 32. And you see in that also we found that the G was there, that is the modulus of rigidity, or we can say the modulus of elasticity in the shearing action. And since you see we are only assuming the elastic deformation, so this G is very well valid, in which the shear stress is proportional to shear strain and the value of G is coming, and it is also the property of material. So which material we are using? Generally we are using the this elastic or this ductile material, in which the percentage elongation is always measuring the ductility property. So this kind of relations which we can easily set up for like the circular solid shaft, and you see the solid, or we can say the solid shaft, but it has to be having a uniform cross section. And the last is the theta, which is nothing but equals to the angle of twist in terms of radius on a length L. So you see, and it has to be uniform as we have already assumed. So with under all those applied conditions, we can say that the T by J is nothing but equals to tau dash by r is nothing but equals to g theta by L. And you see now if we are talking about the this new term, that was the Gj by L or T by theta, we can again define the new term as the torsional stiffness. Stiffness, as you discussed, since we are talking about the spring is there, and whenever it is under the application of torque, it is showing somewhat the twisting part is there, and based on what the maximum shearing stresses are coming, or whatever the size and shapes are there, how these moments can be computed. So for all those kind of things, here we are defining the new term, that is the torsional stiffness, because whenever under the the torque is there, a kind of deformation is there, and we just want to measure the deformation, always the stiffness term is coming. So torsional stiffness, the K is nothing but equals to applied torque divided by this this twisting part, means how much distortion is there. So we can say that this whatever the angular twist is there, or we can say this radial twisting is there, so K is nothing but equals to applied torque T divided by the angular twisting theta. Or once you put those things here, then you will find that it is nothing but equals to, since T by J was nothing but equals to g theta by L, so T by theta is nothing but equals to gj by L. So you see we have either you can compute the torsional stiffness, which is nothing but simply measuring how much deformation is there, or how much you can deform, irrespective whether it is a spring component or whether it is a the circular bar section. It can be simply computed based on what material is there, because G is a property of material. So G into this what is the effective area is there, that means what is the this polar moment of this twisting is there, or inertia is there. So either polar moment of inertia, or we can say the shear modulus of rigidity is there, and then what the total length is there. If the total length is more, definitely see you have this kind of different stiffness is there. So this is, you see, the torsional stiffness is there. It is just to be defined for the torque application. And then we have the last term, that is the power transmitted by shaft, because this is the basic application of any shaft, that if the T is the applied torque and omega is the angular velocity of the shaft, then power transmitted is nothing but equals to P equals to T times of tau. Or we can say the tau, since it is the angular velocity, so we can again describe in terms of what is the rotational speed is there. So tau is nothing but equals to this 2 pi n divided by 60. So once you multiply 2 pi n by 60 into tau, then you have the power transmission, which is 2 pi nt by 60. in terms of watt, or if you are calculating in terms of kilowatt, then we have 2 pi nt by 60 into this 1000, which is like the kilowatt is there, where n is the this revolution of the shaft per minute. So if we are saying that like if you know the rpm of any shaft, then you can simply compute it like the power if you know the torque, or if you know the power that you need to transfer this much power, and if you know that this one speed of shaft, then correspondingly the torque can be easily calculated. So you see here in this chapter we discussed about like that if we have a different kind of like the loading conditions, or I should say that actually if we have a shaft and if I am saying that it is the under of a simple torque or couple or any kind of like the twisting moment is there, and if it is having a uniform cross sectional and also it has the material which is homogeneous in the nature, then you see the kind of relations which we set up is very much valid if the elastic deformation is there under the application of the torque. And you see under that, you see the equation is very well known equation, and this is the basic equation for analysis of any rotating shaft, that is the T by J is equals to tau dash by R is equals to g theta by L. And once you know those things, then probably you can also find it out that what is the stiffness is there of the circular shaft of the or of the spring. So you see it is nothing but equals to T by theta, or we can say g j by L. So that means you see it is depending on g as well as the j also. And once you know like the rotational speed, and once you know either the power or the torque, you can simply find out the remaining parameters. So in this lecture you see we were simply discussing about the rotating shaft, and in the next lecture you see we are going to discuss about that if we have a spring and if we are applying this kind of like the torque and all those things, then what exactly the relations are there in between the shearing stress, shearing strain, and what will be the impact is there of the material of the spring as well as the number of coils. Thank you.
Thank you.